Production of this video was made possible by a 2022 Strengthening, Mobility, and Revolutionizing Transportation grant awarded to the NCRPC by the U.S. Department of Transportation. Flying a drone for bridge inspections isn't just about piloting skill, it's about being a data collector. The aircraft gets you there, but the real work starts once you're in position. Whether you're documenting surface wear, checking for structural integrity, or planning a repair, the quality of the data you collect will make or break your inspection. That means understanding your payload, planning flights intentionally, and knowing how to capture usable, repeatable data. In this video, we're going to walk through the 3 most common drone tools used for bridge and roadway inspections. You have photogrammetry, thermal imaging, and LiDAR, and show you how to get the most out of these. Let's start with photogrammetry. It's one of the most common methods used in bridge and roadway inspections, and for good reason. It's fast, cost-effective, and works with many off-the-shelf drones. Photogrammetry involves capturing overlapping 2D images, then stitching them together into 3D models, maps, and orthomosaics. The better your images, the better your model. When it comes to inspections, a bad model doesn't just look bad, it can miss critical damage. Start with a solid flight plan. Use around 75% front overlap and 70% side overlap as a baseline. If your structure has elevation changes, like a bridge over water or a deep ravine, increase both to 80% or higher. To avoid this, make sure to fly high at a consistent altitude and be aware of your surroundings. Keep your camera angle fixed, usually straight down. For vertical face or bridge supports, add in angle shots around 45 degrees to capture the side detail. Avoid harsh shadows, especially under bridges or near support columns. Mid-morning or late afternoon flights work best because the lighting is soft and consistent. Now, let's talk about camera settings. Turn off autofocus. Set your focus manually before takeoffs and lock it in. Use manual exposure so your camera doesn't keep adjusting during the flight. Stick with a low ISO to avoid image noise. 100 to 200 is usually ideal. Here's something a lot of new pilots miss. GSD stands for Ground Sampling Distance. That's how much ground is covered by 1 pixel in your image. The lower the GSD, the more detail you capture. A GSD of 2 centimeters means you can see small surface cracks. At 5 centimeters, those details disappear. GSD depends on 3 things: your flight altitude, your camera resolution, and your lens. Flying lower gives you better GSD, but it also means more photos. It's a trade-off, but when you need to measure surface damage, tighter GSD can make all the difference. Keep in mind what your final product needs to be during flight planning portion. It really helps with the decisions on GSD. If the bridge deck needs a full inspection looking for cracks, lowest GSD possible will be your best bet. If you just need an update on a project, high GSD would be great for this since it's captured quickly and then processed quickly. If you need accuracy, and you usually do, use ground control points. GCPs are physical markers placed on the ground with known GPS coordinates. They anchor your model to real-world locations. Without GCPs, your model may look good, but your measurements won't hold up. Even just 4 to 6 well-placed GCPs can dramatically improve model precision. To get good results with photogrammetry, follow these best practices. Plan structured flight paths with high overlap. Fly at a steady altitude with fixed camera angles. Avoid shadows and inconsistent lighting. It is often considered better to capture data in full sun or full overcast due to the consistency of lighting. Partially cloudy days can have wide variations in lighting, even in a single flight. Set manual camera settings, use GCPs for georeference to accuracy, and always check your images before you leave the site. One missing or blurry image can throw off the entire model. Photogrammetry is a powerful tool, but only if you fly it with purpose. Now let's talk about thermal imaging, a tool that lets you detect what the eye can't see. Thermal sensors measure heat, not light, which makes them incredibly useful for inspections. They capture temperature differences across surfaces, allowing you to spot issues like trapped moisture, delamination, and electrical problems without ever physically touching the structure. For example, you can identify heat loss in a building, locate cooling water on a bridge deck, or catch a failing electrical junction before it becomes a bigger problem, all by measuring temperature differences. But just like photogrammetry, good results don't happen by accident. Variations in how different parts of the structure absorb and dissipate heat can help identify anomalies such as delamination, moisture, intrusion, or areas of spalling. Repeating this process over time enables tracking of structural degradation or changes, supporting proactive maintenance and safety planning. Next, flight speed. Thermal sensors need time to stabilize and collect accurate readings, so fly slower than you would with a regular camera. Keep your altitude consistent and avoid sudden turns or movements. Quick changes can distort your thermal maps or cause inaccurate readings. Now, let's talk about emissivity. Emissivity is how well a material emits heat, and it matters a lot in thermal imaging. Materials like concrete, asphalt, metal, and water all behave differently when viewed with thermal sensor. Shiny materials like metal can reflect ambient heat, including heat from the drone itself. That can lead to false readings or cover up actual problems. Before your flight, think about these types of materials you're inspecting. It helps you make sense of what the camera is showing you. Always let your thermal camera warm up and calibrate before takeoff. That allows the internal sensors to stabilize so the data you collect is reliable. Then choose the right color palette. White hot is commonly used for spotting heat loss, while iron bow is great for showing surface differences. Whatever you use, lock your color scale if you're collecting data for reporting. That way your temperature range stays consistent from one image to the next. Environmental conditions matter too. Thermal imaging works best in the calm, dry air. Rain, wind, and humidity can reduce thermal contrast and scatter infrared energy, making it harder to see meaningful temperature differences. If conditions aren't good, it's better to wait. Finally, review your data before leaving the site. If the focus was off, if the contrast was too low, or if the palette was wrong, you may have to fly again. It's better to catch that while you're still in the field. Done right, thermal imaging gives you insight into problems that aren't visible to the eye and lets you make better decisions based on what's really happening. And a final thing for thermal, the more time you get out and practice with your specific setup, the better. Every drone and sensor are different, and that can all be ironed out with practice. Now, let's talk about LiDAR. LiDAR stands for Light Detection and Ranging. LiDAR uses rapid pulses of laser light to measure the distance between the drone and objects on the ground. Those pulses create dense point clouds that represent the surface in 3 dimensions. In bridge and roadway inspections, LiDAR is incredibly valuable. It helps map elevation changes, measure grade and slope, model bridge geometry, and identify erosion or structural shifting. LiDAR captures geometry directly, so it works well in areas with low light, uneven terrains, or repetitive structures. But to get good data, you still need to plan your flights carefully. First, think about point density. That means how many laser returns you get per square meter. If you need high detail, for example, to inspect a bridge or road surface, you need to fly slower and lower. That increases your density and gives you cleaner, more detailed results. Next, positioning. LiDAR accuracy depends heavily on your drone's GNSS or RTK system. If your GPS signal is weak or unstable, your point cloud will be noisy or misaligned. So always check your satellite connection and make sure your corrections are being applied in real time. Before launch, calibrate your system. That includes the LiDAR unit itself and the Onboard Inertial Measurement Unit, or IMU. The IMU tracks movement and orientation and helps match the point cloud to your flight path. Without a clean calibration, your entire dataset can drift or warp. Once in the air, fly steady in consistent patterns. Avoid sharp turns, climbs, or dips. The cleaner your flight path, the better your point cloud will look once you bring it into processing software. After the flight, you'll need to process the data using LiDAR software that can handle classification. That means separating ground points from structures, filtering out noise, and cleaning up any artifacts in the data. You may also apply corrections based on the flight log or GNSS data to improve accuracy and alignment. LiDAR produces dense and highly accurate data, but only if you fly it like a surveyor, not like a camera operator. When you take the time to plan your LiDAR mission, the results are unmatched in detail and precision. It's a powerful tool for seeing the shape of your environment and understanding how it changes over time. Let's talk briefly about processing. For photogrammetry, Pix4D Mapper, Drone Deploy, and Agisoft Metashape are 3 of the most widely used tools. They allow you to generate 3D models, orthomosaics, and elevation maps for your captured imagery. Pix4D Mapper in particular is a strong choice if you're also integrating GCPs for high accuracy models. For thermal imaging, FLIR Tools, FLIR Thermal Studio, and Pix4D React are good options. They allow you to visualize, analyze, and export thermal data for inspections and reporting. Make sure you're using radiometric images if you need actual temperature readings, not just visual heat maps. For LiDAR, you'll want something that can handle point cloud classification. Common platforms include DJI Terra, Leica Cyclone, Trimble Business Center, and LP360. Some users also rely on open source tools like Cloud Compare for basic filtering and visualization. Each of these tools has its strengths. What matters is choosing one that fits your aircraft, your data type, and your team's level of experience. By now, you should have a clear understanding of how photogrammetry, thermal imaging, and LiDAR each play a role in modern bridge and roadway inspections. Photogrammetry gives you sharp, measurable visuals for modeling and documentation. Thermal imaging reveals what the eye cannot see, helping you detect moisture, heat loss, and hidden damage. LiDAR captures precise, 3-dimensional data that is ideal for elevation changes, erosion, and complex surfaces. Each tool has its strengths, and each one requires proper setup, planning, and execution. But when used correctly, they give you the information needed to support real decisions. Remember, your drone is just a platform. What matters is the data you bring back. And good data only comes from intentional flights, solid technique, and attention to detail. Your role is not just to fly, It is to collect data that others will use to inspect, repair, and protect critical infrastructure. Fly with purpose, plan with precision, and keep pushing your skills forward. We will see you on the next mission.